Hello, I welcome you all to this another interesting screencast, and the problem reads: the semicircular drainaging pipe is filled with water. Determine the resultant horizontal and vertical force components that the water exerts on the side AB of the pipe per foot of pipe length. The unit weight of water is 62.4 pounds per cubic feet. This problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. Before we start solving this particular problem, let's just explain or just give a brief background of pressure, incompressible pressure. According to Pascal's law, a fluid at rest creates a pressure P at a point that is the same in all directions. So we are saying at any given point within a fluid that is at rest, this particular point receives or is subjected to pressure which is the same in all directions, so that is in equilibrium, right? And this can be represented mathematically by this equation here, where we have P small p equal to gamma z, gamma, which is the unit weight, later on equal to rho gz, where rho is the density of the fluid, g is the acceleration due to gravity, and z is the depth of the fluid. And this equation is valid only for fluids that are assumed to be incompressible. Like in our case here, water, this liquid water is being assumed as incompressible fluid. In all cases, the pressure acts normal to the surface area dA located at a specified point. So like in this particular point here, we expect the pressure to be acting normal. Okay, and it keeps on increasing with depth. Okay, we expect to have the maximum. We are going to have something like this, some distribution like that, right? And this is what we want to find. Okay, of course we can find this using calculus, but to make it much easier, we normally distribute this into two blocks. This one, where we consider the weight of this water here on the wall or the pipe AB, okay, which we call FV, and then we have another distribution like so, okay, and then we call this as our FH horizontal force, and this is what we want to find. Okay, and the magnitude of the resultant force FR is equal to the volume of the loading diagram. Okay, so this is the loading diagram. Okay, this whole lot of it, green and red, and it has a thickness 1 foot, right? And FR has a line of action that passes through the volume's centroid. Okay, the volume centroid for the loading diagram, and not the centroid of the plate, okay, or the surface or the material. Okay, so it's not the like in our case, it's not the centroid of the pipe, but the centroid of the volume of the loading diagram. All right, so let's begin solving the problem like we said. So we are going to divide this into two. We have this portion in red, and then we are going to find what we are calling our FV, which is just basically the weight of the water on that portion. And then we are going to have another part, this one, okay. This is another way of simplifying our work. All right, we have this point here, which is our Q, we call it. Then we'll have this horizontal force here, which is, horizontal force, which is just basically going to be equal to 1/2 q times, if this is our z, times z, like that. Okay, so let's do the calculations. Down, and then we'll put the answers there. So we are saying our FV, if you look at this, we just want to find the density, I mean the weight of that water in a quarter shape of a circle, right? So finding volume for that, so this FV is just basically going to be equal to the volume of the water times the unit weight. Okay, the volume of the water times the unit weight. Okay, is that fine? So for us to find the volume and everything, we have the volume is equal to the area, which is just 1/4 pi r squared, times the thickness, which is b, then times the unit weight, and then we have everything, right? So 1/4 pi, what is r? R is 2, so 2 squared. What is b? It's just a 1 foot. And what's the unit weight? Is 62.4. When we calculate this FV, we get a value of, what do we have? 0.25 by 0.25, that's a quarter by pi by 4 by 62.4. So we get a 196.04 pounds. Of course, we are not finding the location. If you wanted to find the location, then you have this curve that governs the circle. You need to do the integration to find the centroid and so on. Okay, we are not going to do that. We did that already in the other problem. Then let's find FH. We said FH is equal to half times that Q there. This Q is equal to rho times G times Z times B, which is just basically equal to the unit weight, which is rho G times Z times B. Okay, so FH is equal to half times Q, which is this force per unit length, half times Q times Z, which is equal to half times Q times, half times Q is just a unit weight, then Z, there are two of them, Z squared, then times B. This is equal to half times 62.4 62.4 times 2 squared times 1 foot. Have we put everything? 0.5 by 62.4 by 2 squared, of course, by 1. So what do we have? We have a 124.8 pounds. So this is about it. We found FH. Of course, for HS, this one is easier to find where it is located. It's just 1/3 of Z, which is 2. Okay, that's where it is located. For this one, this position here, of course, we need some calculation. Okay, we need some further calculation there. FH is equal to 124.8 pounds. Then FV is going to be equal to, what did we find? 196.04 pounds. Yeah, so this is what we have. This is what we have. We found the horizontal, we found the vertical, and that's about it. Okay, I hope the video was helpful. Let me put this in blue. I hope so. FB is equal to 196.04 pounds and FH is equal to 124.8 pounds. Alright, so I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.